Hi everyone, my name is Rihanna Banerjee, and today I'm going to walk you through three core programming concepts that power our robot in PyBricks: variables, loops, and conditionals. These are fundamental tools that help us write cleaner, more efficient, and more intelligent code. Instead of hard coding every single action step by step, they allow us to simplify our programs, reduce repetition, and make our robot behave more dynamically. I've had the opportunity to apply these concepts through my work with the Unicorn Dreamers FLL Challenge team for over 5 years, more recently with Bolted Bots this past year, and through our GummyBears Robotics education channel, where we break down robotics and coding in a practical, hands-on way. The examples I'll share today are based on what we use in competition robotics. So this isn't just theory, it's real application. With that, let's take a quick look at what we'll be covering today. In this session, we're going to focus on four major components: variables, for loops, while loops, and conditionals. We'll first review what each concept is individually, then we'll combine them into real robot examples. By the end, you'll see how these ideas work together to create structured and intelligent robot behavior. Let's start with a quick refresh on variables. A variable is like a container that stores information so you can use it later in your program. That information could be a number, a word, or even a true or false value. For example, we can create a variable called speed and set it equal to 300 degrees per second. Later in our program, instead of writing 300 degrees per second every single time, we simply use the word speed. When we run the motor for 1 second or 1,000 milliseconds at speed, the program understands that speed means 300 degrees per second. Using variables makes the code easier to read, easier to modify, and much more organized. Now that we understand how to store information, the next step is learning how to repeat actions efficiently. And that is where loops come in. Instead of writing the same instruction again and again, we use loops. A loop allows us to repeat a block of code multiple times automatically. There are two common types of loops: for loops and while loops. They both repeat code, but they do it in slightly different ways. Let's start with for loops. A for loop repeats something a specific number of times. When we write for I in range 5 as our for loop statement, the word range tells the program how many times to repeat. The variable I acts as a counter. It starts at 0, then goes to 1, then goes to 2, and continues until it reaches the number we've set. But it starts and stops just before reaching 5. So this loop runs 5 times. If we place a turning motor command inside the loop, the robot performs that movement 5 times automatically, without us having to write the command 5 separate times like on the right. This is extremely efficient, especially in FLL, where repeating movements accurately is critical. Before we run movement code, though, we always need to start with a proper setup. To use loops to move our robot, we need to properly initialize our hub and motors. We import prime hub, motor, and drive base, but usually this automatically comes when you open a new code in PyBricks. Then we assign motors to ports. In my example, port A and port B are my motor ports. Again, this will completely vary based on your bot design. You should always check your code and ports before running. We also need to define important physical measurements like wheel diameter and axle track. These values affect how the robot calculates distance and turning accuracy. Without correct setup, even perfectly written loop logic won't work properly. Now that setup is complete, let's look at a full for loop code. In the example here, our for loop statement is for counter in range 5. The counter is the variable and the I in the scenario. Each time the counter increases, the robot moves back and forth. It waits, then beeps. This repeats 5 times. After the loop finishes, we display done on the hub. Notice how short and clean the code is. Instead of writing that sequence 5 separate times, we write it once inside the loop. This is what makes for loops so crucial in robotics programming.
Watch closely. What's really happening here is that the loop is handling all the counting for us in the background. We don't have to manually increase anything. The structure of the for loop takes care of it automatically. That's why this pattern is so reliable. We know exactly how many times something should happen, and a for loop keeps the program simple, predictable, and easy to read.
Next, let's explore a loop that runs based on a condition rather than a fixed number. While loops. Sometimes we don't know how many times something should repeat. So instead of repeating a fixed number of times, we want the robot to continue moving until something changes. That's where while loops come in. A while loop keeps repeating code as long as a condition is true. For example, we can write count equals 0, and then while count is less than 3. The program checks the condition while count is less than 3 each and every time it's run. If it's true, the code inside the loop runs. After running, we update the counter. Once the count reaches 3, the condition becomes false, and the loop stops. So instead of saying repeat exactly 3 times, we're saying repeat while this condition is true. In real FLL missions, we often don't know how long the robot needs to move forward. Instead, we can want it to keep moving until it detects a black line. So the condition is, keep driving forward while the surface is not black. The moment the sensor detects the black line, the condition becomes false and the robot stops. In FLL, while loops allow repetition based on logic and sensor feedback, not just a fixed number. And that flexibility is critical in competition robotics. Now, let's look at a real robot example using a while loop. This is something you can absolutely try at home. In this example, we introduce 2 variables, counter and target. The counter is the value that changes each time the loop runs. The target is the value we eventually want the counter to reach. Our loop condition says, while counter is less than target. So the robot keeps repeating its actions as long as the statement remains true. Inside of the loop, the robot performs a sequence of actions. It moves forward, moves backward, beeps, displays text, and then increases the counter by 1. In each cycle, the program checks the condition again. If the counter is still less than target, it will repeat and keep on going. Once the counter reaches target value, the condition becomes false, and the loop stops automatically. So, if the target were set to 5, the robot would complete that full sequence 5 times before displaying that it has finished. What makes this powerful is that we're not hard-coding 5 separate movements. Instead, we're defining a goal and letting the loop manage the repetition. This structure is extremely useful when we want controlled repetition based on a defined objective.
Observe. Each time the robot completes a sequence, a counter increases in the background. You don't see that variable changing, but it's controlling everything. The loop keeps checking. Have we reached our target yet? The automatic checking is what makes loops important. The robot isn't guessing how many times to move, it's evaluating the condition every single cycle. And that's controlled repetition in action.
Now that we've seen how to repeat actions in different ways, let's take the next step and look at how robots make decisions. Conditionals allow the robot to check a condition and choose what to do based on whether that condition is true or false. For example, we can create a variable called direction and set it equal to left. Then we can write a conditional that says, if direction equals left, print turning left in the console. Otherwise, or else, print turning right in the console. The program first checks whether the condition is true. If it is, it runs that block of code. If not, it moves to the else statement. This allows the robot to decide actions based on a situation. We use this constantly in robotics, for sensors, direction changes, alignment, and more. We use conditionals in everyday life all the time as well. For example, if a cabinet is closed, we open it. If it's already open, we just grab what we need and close it again. That's decision making based on a condition. Now let's see this in a real robot example. We create a variable called move forward and set it to true. Then we write, if move forward is true, drive forward. Else, drive backward. The robot follows that logic for 3 seconds and then stops. If we change move forward to false, the robot immediately switches direction. This shows how crucial conditionals are. They allow one small change to completely alter robot behavior.
Look, guys, what is important here isn't just the movement, it's the decision. Robot behavior isn't hard-coded to go forward or backward. In this case, it's checking a condition and responding to it in real time. One small change in a variable completely shifts the robot's behavior. That flexibility is what makes conditionals powerful.
Now, let's combine everything into one final example. We want to create a zigzag movement by combining variables, loops, and conditionals into one program. First, we set a variable for motor speed. Then we use a for loop to move forward multiple times. Inside that same loop, we use a conditional to decide which direction to turn. If the loop number is even, like 0 or 2, the robot turns left. If the loop number is odd, like 1 or 3, it turns right. To pivot, we run the left and right motors in opposite directions. The result is a zigzag path. This path demonstrates how variables store data, loops repeat movement, and conditionals control direction. Together, they create structured, intelligent robot behavior. Here, one single program combines all these. When you run it, the robot should move forward and alternate left and right turns, creating a zigzag path.
This is where everything connects. We're no longer using loops or conditionals on their own, we're layering them together. The loop controls the repetition, the variable manages speed, and the conditional determines direction. What makes this powerful is that the robot isn't following a pre-drawn path. It's evaluating each step as the loop runs.
Thank you so much for listening. Today we covered variables, for loops, while loops, and conditionals. These are the foundational tools we use in competition robotics and real-world programming. If you'd like to explore more robotics content, coding tutorials, or STEM challenges, you can check out our website at GummyBearsRobotics.org. Feel free to email us or check us out on Instagram too. We would be happy to answer any of your questions. Thank you so much, and see you next time. Bye!